Boston shirt.
Yeah. Alright, I'll do a couple examples of what we finished with yesterday.
So he said this question is bunch of hello? Yeah, I know. This is hello.
No. What? I should have taken both.
No, I have. Just I don't have it on my
Having that, it's
I think the best.
it's the best.
You never had a sale?
Six.
I got interviewed for we do like a little hype video before you
Like all my homework, and it just ends. I actually have a I'm sorry.
Alright, so if you guys remember from yesterday, these were the two problems that we had. Okay, these are the issues that are created in regards to our domains. Our issues are created by these two concepts, okay, these two procedures. We can never divide by zero, right? We can never take even roots of negative numbers. Those are the only things. So if I ask you to divide by 100 million, you should be able to do that, right? That should not impact our domain. If I ask you to take the cube root of an expression, that should not impact our domain, okay? And we, at the onset, always make the assumption that our domain is what? All real numbers, okay? We would make the assumption that there is no problem, and then we systematically go through and try to find if there are problems, okay? Then we remove those if necessary. What happens is that both those things have to be met, okay? Because some of our functions that we see will have division by zero, and they will have even roots of negative numbers, or the potential for that. So we need to make sure that we meet both criteria, that we exclude all x values that would create those two operations or algebraic processes to occur. Okay, so I'm gonna do a couple examples here. First one, not too bad. We've got f of x is equal to x plus 2 over x squared minus 1. Okay? So in this case, because we've got x squared minus 1, we have the potential that there could be division here, right? Division by 0. So what do we need to do to that bottom? Examples we did yesterday, we just did this, right? Take that denominator, say it cannot be 0. Okay? And I told you yesterday when we talked about these types of equations, we put this does not equal sign, we still treat it like an equation, right? We go through and solve it. It's just an identifier at the end that says, hey, this is, usually these are the x values that we're interested in. These are now the x values that we're interested in that we want to kick out. Okay? So how does that work? How do I find values for x that do that? Can I factor that? Okay. Can I go x plus 1, x minus 1? Yeah, it's not the only way we could do that one. Can I take square root of both sides? Yeah, that might have been quicker. Add the 1 to both sides and then take square root, but either way is fine. I gotta be plugged in my tablet keeps dying, guys. Okay, so that tells us that x plus 1 cannot be 0, x minus 1 cannot be 0, so x itself cannot be plus or negative 1, right? Okay. So when we write our domain, okay, our domain, make the assumption it's all real numbers, but now we got to kick those values out, right? So on my number line, okay, and maybe a quick sketch of the number line might be a good thing to do to make sure we get this interval right. You know, negative 1 might be there, positive 1 might be there. There has to be open dots there, right? They have to be removed. But then if I assume all real numbers would be everything then that is red, correct? So how do I describe that? Well, the first value that I come across that would be red would be negative infinity, right? as I move through my number line, the first problem I come to is this -1. So I write that number down. But I need to kick it out, right? I need to exclude it, so we put that parenthesis. And that means I can get to -1.0000000, as many zeros as I can in a 1. I can get right up to -1 on the left hand side, but I can't get there. And then I got to jump over 1, or -1, right? So that means now that I can, this here says that you can get to -0.9999999999999 as many times as you say 9. But you can't get to -1 from the right hand side. And now what will be the next value I come across as a problem? 1, right? So this interval, right here, this first interval is saying all of these values are okay. The second interval is saying all of these values in here are okay. And my third interval should be then 1 to infinity, right? And that is then saying that all of these values over here are parts of my solution. Okay? So here's the thing. If I've got 2 values that I kick out, think about what happens to your number line. It breaks your number line into 3 intervals, right? If you had 3 numbers that you had to kick out, it would break your number line up into 5 intervals. Okay? So the more numbers we have to kick out, the individual numbers like this, okay, these domains written in interval notation might get lengthy. Okay? But if we can understand how to kick one value out like we did right here, kicking -1 out, we should be able to do the same idea, same concept, same procedure by kicking out 2 values, 3 values, 4 values, however many we need to. Another way of doing this, I mentioned it yesterday with you guys, is that we can use what we call set builder notation. Okay? Now, for the most part, I'm not going to ask you to use set builder notation, but I am going to ask you to be able to read it and understand it. Okay? Because there's going to be text that I give you, there's going to be PowerPoints that I give you, PDFs that I give you. You might get in another class and that's all they use is set builder notation. So I want you to be able to be fluently able to read the math. Okay? If I can't read the math, and the other words that I can read don't matter to me. Does that make sense? If I start reading like a paragraph theorem or something like that, and I can read every single word in there, but when I get to the math notation, I can't understand what they're trying to tell me with the math notation, then all those words that I read in the paragraph that I did understand don't matter. Does that make sense? Okay? You got to know both parts. All right? So what we do is we write it this way. Okay? If I want to go what we call set builder notation, put a brace there, and the brace just says that what is about to come after this is a set of objects. It's a collection of things. Okay? A group of things. We then have to identify, well, what kind of things are we talking about here? We're talking about X values. Okay? You know, if my collection of things was flavors of ice cream, I'd write flavors of ice cream there. Okay? But my things here are X values. And then we write that vertical bar. And that vertical bar is another shorthand notation that stands in for the phrase such that. Okay? So X such that. All right? Now I'm going to say X. So now we start telling you what are the conditions that X needs to meet. Okay? I'm going to write X as an element of all real numbers. I'm going to say X belongs to the entire number line. Because that's the assumption we set out with, right? That X is all real numbers. Okay? But, so put a comma or a semicolon here, but X cannot be plus or negative 1. Okay? And I think that's a little bit more user-friendly when I'm trying to write things out by hand. And I don't need a graph to figure that out. The algebra tells me right away that plus and minus 1 are not answers. They're not values that are going to work. And that might be a quicker way of describing my answers. Okay? But again, web assign, because that X is an element of all real numbers, there's a lot of different ways of doing that. Okay? And web assign is not going to have all the programming in the background to adjust for the way that maybe I write it compared to the way maybe Tyler writes it compared to maybe how Emily writes it or something like that. Okay? And to be honest with you, sometimes this is fine as well. We write X such that X cannot be plus or minus 1. Okay? If I write X such that X cannot be plus or minus 1, the fact that I've left out what X can be tells me exactly what X can be. It can be everything except for plus or minus 1. Does that make sense? Okay? So those are alternative ways of using our different notation to describe the same types of answers. All right? And like I said, I want you to be able to understand that and read that, because you will get to a calculus class where that's what's used. Okay? We will get to aspects of this course where that's what the author wants to use. Okay? So we go with that example. Let's change it a little bit. Let's change it ever so slightly. Change that to a plus sign. Okay? That's all we change right there. Change it, x squared plus 1. Now if you're a robot, if you're not paying attention, you're just saying, oh, I got division, so I got to make sure everything's not equal to 0. I say x squared plus 1 does not equal 0. I go through, I subtract 1 from both sides. I got x squared does not equal negative 1. I take square root, and I say x cannot be plus or minus I. Okay, so x cannot be plus or minus I. X cannot be an imaginary value, right? Well, what does our domain start off with? All real numbers. Is I one of those things? No. Okay? So even though x cannot be that, that's great, that's fine, but it's not even a choice at the onset of the problem, right? So my hopes are, because that might take you maybe, I don't know, 30 seconds to do. My hopes are that you realize that you look at this before you do anything, and you look at that x squared plus 1, and you think, well, x squared is going to make any number that I choose positive, right? Okay? And then if it's any number that's positive, that means it can't be 0. Okay? Well, it can't. Okay. It's going to give me 0 or anything that's positive. But the instant that I add something to it, doesn't it take it away from 0 or make it more positive, right? So is there any way that I can ever get 0 in that denominator? No. Okay? So there, my hopes are you just look at that. You don't even do any algebra. You do math, because that logic of saying, well, x squared plus 1 can never be 0, I'm doing math, but I'm not doing any algebra, I'm not doing any arithmetic or anything like that. And my hopes are that you can do that question, find that domain to be all real numbers, almost instantaneous, and you go to the next problem. Does that make sense? Okay? That's the idea that, I think in previous courses we've been trained to do this procedure to this type of question. We do it over and over. We do it 20 times in a row on a homework assignment. Okay? Without thinking, after we do the first 2 or 3, without thinking what the fourth one looks like, what the fifth one looks like, we just do the procedure to the values and expressions that are there. Hopefully now we start to kind of incorporate some thought before we do any of the work. Okay? Because a lot of times it's going to pay off if you do a little thinking prior to doing work. I talked to my geometry kids the other day, thinking about in life, and if I go through everyday actions, everyday life, and I just do things without thinking about repercussions and thinking about consequences or anything like that, am I going to probably end up in jail at some point? Yeah, you're gonna do harm to something, yourself, someone else, something like that. Okay. Same thing in mathematics. If I don't have any thought, I just do, then I'm going to probably harm my math skills. Okay. I'm going to waste time. I want to do those types of things. So we always want to be thinking about repercussions, thinking about foreshadowing, that kind of stuff before we get into doing the actual arithmetic. Okay. All right. So let's do another one. Let's do. I'll give you a good one here. Let's go f of x is equal x to the fourth over x squared plus x minus 6. All right, so we got division here, right? What's the number one thing you can never divide by? 0. Okay? So hopefully you're seeing the purpose of why we spent some time in dealing with factorization, okay, factoring quadratics. Because now I'm going to take x squared plus x minus 6 and say that it cannot be 0, right? If it cannot be 0, okay, I'm still going to factor this like I normally would. What's that going to factor to? Say again? X plus 3, x minus 2? Cannot be 0. Okay. So x plus 3 cannot be 0. X minus 2 cannot be 0. So x cannot be negative 3. X cannot be 2, right? So, and I'm gonna try to urge you to think about this way. If you struggle with it, obviously draw the graph. But I want you to start thinking about how we come across this interval notation without developing the graph. Because again, we want to be efficient with this stuff. So, which one of those numbers comes first in the number line? Negative 3. So, we assume all real numbers. So, if I assume all real numbers, you know, that would be kind of the setup of that interval, right? All real numbers. But now I got to go through there and kind of delete the numbers out that are being represented down here. So negative 3 is that first number I've got to kind of delete out. So I do that. Okay. Give myself a little bit more room here. Okay, so if I delete that one out, I just want that one gone. I don't want the one to the left of it. I don't want negative 3.0000001 gone. And I don't want negative 2.9999999 deleted out. So we have to do something like that, right? And now we can go through, okay, so that interval right there, the way I've got that set up, is saying that 3 is the only number you've kicked out of all your real numbers. But what other number up there says we need to remove it? 2. So then I put, okay, next one's 2, union, and then 2 to infinity like that. And that is going to effectively then kick that 2 out, right? And if we look at those 3 intervals, okay, and the union of them, they are in order. Okay, go from negative infinity up to negative 3, and then you go from negative 3 to 2, and then you go 2 to infinity. Okay, you are in order chronologically left to right, and that's describing the removal of those 2 points. Okay, those 2 x values. Is that something we can do? Does the numerator have any impact here? Does the numerator ever have any impact? See some head shaking, no. What if the numerator had a root in it? Would that be an impact? Yeah. So if I had, you know, for instance, let's say I put square root here. Okay? Now the square root of x to the 4th is just square root of x squared, right? Or, sorry, it's just x squared. But I would not be allowed to put negative numbers in there, right? Okay? So that would maybe be something that we have to pay attention to. Okay? And realize then, well, in this interval there are negative values. Can I adjust for that so that I don't have negative values? Okay? We'll do one from the beginning here. So let's say that I've got so let's say g of x is equal to square root of x over 2x squared plus x minus 1. Okay. So when we look at this, guys, we've got both these things going on. We got the potential for division by 0. Okay? Because if these two values is 2x squared plus x, if they arrange themselves in a manner that they provide me 1, and I subtract 1 from that, I get 0, right? So I could maybe have 0 there. And I've also got roots. So both of these things have to be abided by in regards to the right of my domain. Okay? I can't just choose one and say, I'm just going to deal with the numerator and say that one's greater than 0, then I'm done. Okay? And I'm not going to just choose the denominator and say, well, that one's whatever those x values are, and I'm done. Okay? I have to understand that both conditions need to be met. Okay? So we know that radical x, okay, the number underneath there has to be greater than or equal to 0, right? So x has to be a positive number, okay, or 0. So x greater than or equal to 0. Now that's nice because there's really no algebra to do there, right? Okay, I've now got my domain there. But we have the idea that and 2x squared plus x minus 1 is not allowed to be 0. It cannot be 0. And again, we get another situation of why we spent time on factoring. We have to do the AC method maybe here, right? Wait, -2 or two numbers multiplied together give me -2 back, give me 1. -1 positive 2, right? So I'm going to rewrite this as 2x squared plus 2x minus 1x minus 1 cannot be 0. Remember, group in the first two, group in the last two. So give me 2x, x plus 1. Take out a -1 out of both these. Give me x plus 1. Cannot be 0. So we get those things, right? So what we have to make sure that we do is that we incorporate in our domain, if we say our domain is all real numbers, okay? That's what we always start off with. Domain is all real numbers, okay? Maybe you can do it this way. Maybe you, if you're more of a picture type person. Okay, so my domain is all real numbers. I'm going to put in here just some key values. We have 0, -1, and we have 1/2, right? So maybe I put those values in. And now this condition and both those conditions need to be met for us to describe our interval, right? Well, if I say x has to be greater than or equal to 0, can I just kind of do that and say that's right now, based off that first condition, the only values that I'm allowed to choose? Does that make sense? Okay. So I kick those out, I delete those out, say, okay, now that's my solution set right now. But in that solution set, one of these values still remains, right? That 1/2 is still up there. If I plug 1/2 in here, square root of 1/2, I can do that. But can I take square root of 1/2 divided by 0? No. So you see how the x value that you choose has to give me a positive number up here, and it has to give me a non-zero number right here. Okay? So 1/2 needs to be deleted as well. Just put an open dot there to delete that. Okay? And now from that number line, can we write down our domain? Can we say from 0 up to 1/2, we're okay. I want to kick out 1/2. And then that thing should be our overall domain. I'm going to graph this for you real quick while you're writing that down. Square root of x divided by 2x squared plus x minus 1. All right, so we're looking at that graph right there, correct? Okay. I'm going to come over here. This is that graph. Do you see how it's not existing over here to the left of 0? There are no y values being plotted for values left of 0. Okay. The only values that we're interested in are those to the right of 0. So we said that x has got to be greater than 0. But if I ask this thing to evaluate at f of 1/2, oh, I'm using g, sorry, g of 1/2. It gives me that back, okay? Meaning that when I plug 1/2 in, I get a value that is undefined. Does that make sense? Infinity is undefined value. We don't know what it is, okay? Any other value that I plug in will give me something numerical back, okay? If I plug in, just to prove the point, g of a number really close to that, 0.499999, right? That'd be really close to 1/2. Do I get something back? Okay. If I try g of 0.499999999999, do I get something back? Okay. And if I try g of like 0.50000000000001, do I get something out? At some point, GeoGebra will, kind of like every other calculator, kind of blow up on us, and not know what to do, so because I use too many decimal places there. But the idea is that it should. There we go. Okay. So basically, what I was doing is saying that you exceeded our power. If you do it on your TIA 3 or 4, it'll give you it's called an overflow error. Basically, it doesn't have enough memory or RAM to do the operation I'm asking to do. There are other programs, a program called Mathematica or Maple, that will allow me basically to plug in any value that I can think of because they're so powerful and will take things back. Does that kind of make sense? Okay. 0.5 is the only number that doesn't work. We got to kick that out, and obviously then the numbers to the left of 0. I think those are pretty obvious, so we have to kick those out. Let's do one that doesn't require too much work. Let's say that I give you f of x is equal to then the cube root of 2x squared plus 1. 2x squared plus 1. Any problems there? What are the only issues? Division by 0. Do we have division here? Even roots of negative numbers. Do we have an even root here? No. Okay. So we at the onset we start with the idea that we're looking at a domain of all real numbers, and then we see if any of those two things are occurring. If they're not, then there's nothing that gets kicked out, right? Okay. If we were to graph that, show what that thing looks like here. Now, there's not a cube root. Your TIA 3 or 84 has a cube root command on it. This does not. I had 2x plus 1 underneath there. If I want to cube root that, I have to raise it to the 1/3 power. And I need that 1/3 to be in parentheses. So you see there that there are no x values that need to be kicked out, right? Now, if there was division by 0, you would not see that. They would not put an open dot. None of your technology will do that. So I guess what I'm saying here is that this here can be easily determined from your graph. If you've got division by 0, your technology is probably not going to show you an open dot. Does that make sense? So you would still need the algebra to validate that. Let's see what we can do. Let's go to let's get an idea algebraically what this would look like. Let's say we take the cube root. I had 2x squared, so it doesn't matter though. Let me show you what that would look like. 2x squared. Still the same kind of concept, right? Negative infinity to positive infinity. Nothing's getting kicked out. But what if I wrote something like this? Now do we have division? Now we have division, right? So that cube root is something that I don't want you just to look at and say, oh, I got a cube root. I can automatically just say the domain is all real numbers. If I look at this thing, let's graph that. 2x squared plus 1. And then I have that divided by x plus 1 underneath the root, right? So then even more parentheses goes off. There we go. See what that looks like. And that's what it looks like, right? That's what I was looking for. It's to be cube root. Okay. You see kind of a weird thing happening. Now that the graph, just I'm zoomed out a little bit, just kind of disappearing there as I scroll down. It's just a graphics thing. There's something happening here at -1, isn't there? Okay. So even though this thing's under a root, f of -1 still gives me an undefined value. So we still have to abide, even though this is a cube root, and this one here, because it was a cube root, we said, well, nothing got kicked out. This one incorporates division, so the division has to be met. That condition has to be understood, right? Okay? So we say x plus 1 cannot be 0, and so x cannot be -1. We write our domain based off of that. Is that something we can do? I think that's No, let's do one more. One more and we'll get into something else. My hopes are that as we start doing problems like this, you start to see the benefit of the structure of the class and why we've done some of the procedures, some of the algebra earlier, just pure algebra, so we can address maybe a question like this. Because what does x squared minus 2x minus 8 have to be? What kind of numbers does that have to be for this domain? To determine my domain. It has to be positive. Okay, can it be 0? Yes. So we write that, correct? Now, if you remember a couple days ago, we were talking about the end of one of our homework assignments, there were a handful of questions like this. And we had to set up a sign chart. Okay? The purpose of learning that and talking about that was so we can address this aspect of the course. So we can address domains. So what we did is we factored this. We write it as x minus 4, x plus 2, greater than or equal to 0. Once we do that, then we create our sign chart. If you remember, our sign chart said find the zeros that are coming from those factors. So one of those zeros is -2, one of those zeros is +4. And because we have equality here, I'm just going to remind myself that those need to be closed dots, and we can use those values. So when I write my interval notation, they're going to be brackets. Okay? You remember then that we kind of broke up our number line into 3 regions like that. We wrote our factors over here, x minus 4, x plus 2, and then our total. And ultimately, this little system that we're setting up here is basically going to tell me whether x squared minus 2x minus 8 is giving me a positive y value, something above the y or the x-axis, or is it going to, when I plug in that x value, is it going to give me something below the x-axis? So I plug in values over here that are left of -2. I like to choose just absurd values. -100 million. Remove 4 from that, or add 2 to that, you still have something really, really negative. So negative gives me a positive. Those real absurd values allow me to understand that those values of -4 and 2 are minuscule. They're very minute and useless with very, very, very large numbers. Now I can't do that here, but there is a nice number of 0 in there that I can use. So I plug in 0, I get negative, positive, right? And that total should be negative. And then to the right of 4, I'm going to try 100 billion. Well, remove 4 from that, you're positive. Remove or add 2 to that, you're still positive. And my total is positive. Okay? So remember doing that, then we looked, okay, what did the inequality say? We had to be greater than or equal to 0. This phrase right here, greater than or equal to 0, is saying we are looking for positive values. We want the x values that plug in here that make this positive. Those are this x value here, this set of x values, and that set of x values, right? Come to my number line, it's those. Numbers left of -2, it's these, which are my numbers to the right of 4. Write that interval notation. Be -infinity to -2, union 4 to infinity. I messed up. Okay. Make sure that we know that we can use the 2, and we can use, or -2, and we can use the 4. So we got to put brackets around this. Okay. That's going to be the interval notation for that thing. If we were to graph it, if you're struggling with these things, guys, struggling coming up with the solutions algebraically, figure out what the answer should be before you do anything. Okay? Grab my graphing tool, whatever you're going to use, and graph square root of x squared minus 2x minus 8. Now, like I said, it's not going to give you holes. If you got division by 0, that might not be always showing you everything you need, but it's going to give you a pretty good idea most of the time. If I look at that, can I look at that graph and decide that the domain is going to be from -infinity up to -2, and then from 4 to +infinity? So before I do anything in algebra, I know the answer. Okay? Now the question is, how do I go about doing it? Can I mimic the math, use the math to validate that? Okay? On tests or quizzes, guys, this is not enough. Okay? This is not your work. Okay? It's the calculator's work, right? You need to show me on a test or quiz this work. Okay? I think that should be enough examples to help you get through that homework assignment. Let me change something real quick here in this one though. It's important to talk about. What if I do this? What if I just put 1 over x squared minus 2x minus 8? Do I still have to take the x squared minus 2x minus 8 and say that's got to be positive? Right? Okay, I still can't take the square root of a negative number even if it's in the denominator. Okay? But now that I put that thing in the denominator, what other number is now a problem? 0. Tyler's saying 0, right? So what would that do? How would that change my interval? It would just kick out negative 2 and 4, right? It would make me put parentheses around those things or open dots on the graph. Okay? So when you have a root in the denominator, okay, 0 needs to be kicked out as well. So you need to make sure you say greater than 0 instead of greater than or equal to 0. Okay? If it's a 4th root, 6th root, 8th root, guys, you still do the same algebra. You don't even pay attention to, there's nothing different to do if it's a 4th root compared to a square root, or a 6th root compared to a square root, okay? You still take the radicand, make it greater than or equal to 0, or if it's in the denominator, you make it just greater than 0. We feel comfortable with that? All right. Every year I ask that question. We feel comfortable with that. And then on a quiz, we show that we have maybe not the greatest comfort level. So hopefully maybe you guys are going to change that pattern for us here in the near future. All right. That gets us into the next concept that is directly linked to this, directly linked to domains. I just got to find out where it's at here in my wrong PowerPoint. All right, and it's graphing what we call piecewise defined functions. Piecewise defined functions. A lot of times it's called piecewise functions. Okay. The main thing here that we need to understand is the word piece. Okay? We're going to see pieces of functions. We're not going to see the whole thing. Okay? We're not going to graph the whole thing. We're only going to graph it based off of the interval that it's defined for, the interval that they're asking us to graph it for. So you guys have graphed x squared a lot, right? And you graph that for, if it doesn't say, the lack of telling me the defined domain, we use all real numbers. Okay? It's going to change a little bit now. Now we're going to say, okay, let's look at x squared, but let's only graph it between maybe -2 and 12 on the x-axis. So then we go find the respective y values that are associated with that kind of stuff, all those values, and we graph just that piece of the function. Does that make sense? Okay? But it gets sometimes kind of hairy, kind of messy, because we can then do that with another function on top of the same graph. Okay? As we're doing these though, we might have 3 or 4 or 5 different rules that we're trying to graph on the same XY axes. What I want you to understand is that because they're called piecewise functions, the curves should never overlap. Okay? Because if they overlap each other, okay, they share same y values for the same x values, or not the same y, they share different y values for the same x values, we would fail the vertical line test. So these are functions, remember that. And they should, when you're done, should pass the vertical line test. Okay? So this is what I have. This is the way we define them. I'll just flash this up here real quick for you. Piecewise defined function is defined by different formulas on different parts of its domain. Okay? So we'll start with the whole number line. And we'll say, okay, this section of the number line, we only want to graph x squared. This next section, we only want to graph maybe x cubed. This section, we want to graph 2x plus 5. Okay? And we'll do that in those 3 sections or those 3 domains. And then look and see what our overall graph looks like. Okay? And there's a lot of things in real life that we can model with piecewise functions. Okay? We'll talk about some tomorrow specifically, some modeling of piecewise functions. All right, so what this notation is going to look like, don't let it scare you. A lot of people look at it and say, oh, that's a lot of like gibberish, and it's scary looking, so we shut down right away. It's not something you guys can't do, and you've been doing it. So you guys have graphed x squared before, right? Did that for probably a year and a half already, okay? You took an entire year of Algebra 1 and worked on graphing things like 2x plus 1, right? And they told you when you graphed x squared and you graphed 2x plus 1, you got to choose the x values that you plotted and found y values that associated with them, right? And you could do any points that you wanted to. X squared, you usually use like 3 or 4 or 5 points. 2x plus 1, you only use 2 points, right? And you learn those little things about how to graph these different types of functions. Now, it's the same exact thing, but they're restricting you on which x values you're allowed to choose. Okay? So if I want to graph x squared if x is less than or equal 1, and 2x plus 1 if x is greater than 1, this is how we go about doing this. Okay? I'm going to cut that out. I'm going to put it on here and graph it on here. So let's see here. All three. Come on. Let's write it. So we had what did it say? F of x was equal to, it said x squared if x was less than or equal to 1, right? And it said 2x plus 1 if x were greater than 1. Okay? We're going to graph those things. Okay? We're going to look at, you guys know what x squared looks like, right? Okay, x squared in general, go back to Algebra 1, Algebra 2, it's that guy right there, correct? Okay? Well, if I only want this to be defined for the numbers that are less than or equal to 1, then there's part of this graph that we need to erase. And this is how you guys go about doing this, okay? I always kind of look at my rule first, or my restriction or condition first. And that's this thing right here, okay? So that's my condition. This is my rule that I apply with these x values. If I choose x to be 1, I get that point back right there, right? Now if I choose values that are less than 1, okay, so if I choose a half, I get a fourth back. If I choose 0, I get 0 back. Choose -1, I get 1 back. Choose -2, I get 4 back, right? And these are all x values that are less than 1, right? Less than or equal to 1. So what's going to happen when I start filling all of those in, just like graphing this thing all the time, you're going to get that portion of the graph. That is a piece of x squared, isn't it? And it's the piece that has only been defined for values that are equal to 1 and less than. So once you graph that, you then go to the next equation and you graph that. So we're looking at now y equals 2x plus 1. Okay, now that's a line, right? Okay, so with anything that's nonlinear, you're going to need a handful of points. Okay, I used, 4 there. Okay, some you might need 5, some you might need 6, that kind of thing. But for a line, how many points do you need? You need 2, right? Okay. Now it says x has got to be greater than 1. So the first number that's greater than 1 is the number we have to use. We have to use 1.00000000, infinite number of zeros and a 1 after, right? If I plug that, and if I multiply that number by 2, then I get a 2 with an infinite number of zeros and then a 2 behind that. Does that make sense? And then add 1 to that. Don't I get 3 point infinite number of zeros and a 2? Does that make sense? So is that number pretty close to 3? So instead of using 1.0000000001, because that's hard to do, that's kind of ridiculous, we're going to actually use 1. We're going to use the one, even though it says greater than, we're going to use that 1. And then when I graph it, what am I going to do when I graph it? Any ideas? So if I use 1, what's the y value I get back? And 2x plus 1. You get 3 back, right? But this thing should not be defined for 1, so I should not get 3 back. It should be defined for 1 point, infinite zeros, and a 1, right? So when I do that, I get 3 point, infinite zeros, and a 2 back, right? Was that pretty close to 3? So we evaluate this thing right here at 1, and we get 3. And we go to 3, and instead of putting a solid dot, we put an open dot, right? Does that make sense? Okay? And that's showing us that we're not using 1, we're using the number right to the right of it, and we don't get back 3, we get a number back that is right above 3. Does that make sense, everybody? Okay? So now, how many other points do I need? I need 1 more point, right, for a line. So I choose any other point that is bigger than 1. Choose 2, choose 3, choose 4. Use something, don't choose 100, because then I got a graph out there. I'm going to choose 2. So I'll plug 2 in here, what do I get back? 5. So I'll plug that point. Okay? And my calibration is all messed up on this thing, so hold on. 5. There we go. So now that is what we call our piecewise function. Okay? You see how it's separate pieces of different functions? But it's still a function. If I say x is equal to a, get this little vertical line in here for us. And grab it, behind all that stuff, okay? Do I pass the vertical line test in all these spots here? The only issue that might arise is right there, correct? But that open dot tells me that this red line is actually coming up to, but not getting to that, right? There's open dot says that's going to pass, that vertical line is going to pass right by it, okay? We're really close to it, but we don't get to it. So we're only intersecting 1 time there, right? And then to the right of that, still only intersecting once. So when you're done, you should always be able to run your vertical line through there and still have a function. You should never have a y value at 1 in this case that has, or sorry, an x value of 1 that has 2 different y values being defined. Okay? We'll spend a little bit of time with piecewise functions tomorrow. I said we'll talk about a piecewise function that you guys are maybe